Alabama STEM Explorers is made possible by the generous support of Hudson Alpha Institute for Biotechnology, Southern Research, solving the world's hardest problems, the Holly Family Foundation, Alabama Works, Alabama STEM Council, Alabama Mathematics, Science, Technology, and Engineering Coalition, Alabama Math, Science, and Technology Initiative.
Perfect. Speaking of perfect, I found these amazing flowers in the yard. I think my mom will really like them. I was kind of wondering why they were all different colors though. I think I know someone who can tell us. Follow me. Hi, and welcome to Alabama STEM Explorers. I'm Anderson.
And I'm Kathryn.
And we're at Southern Research today in Birmingham, Alabama.
And Anderson was just telling me about some flowers that you picked for your mom, right?
Yeah, so I saw these flowers on my counter and I looked really closely and I noticed that all of them are different colors and I was wondering why.
So to answer Anderson's question, I thought we would start today with a magic trick.
A magic trick?
Yeah, a magic trick. So what I have right here is a tea kettle, but it is not just any ordinary tea kettle, it is a magic tea kettle. And this kettle will pour whatever color I tell it to. Do you believe me?
I don't think so.
Well, let's check it out. All right, so say the magic words.
Alakazam?
That works. All right, Mr. Magic Tea Kettle, I say to pour pink. Oh, that is pink like my shirt. Okay.
Well, you could have just put pink dye in there.
Maybe I could have. Maybe this water was already pink. So I think pour light pink. What do you think? Light pink?
Well.
Oh, how about some purple? What is going on? Okay, now I want some Southern Research blue. How about that? Southern Research blue. Pretty close to Southern Research blue. All right, I love turquoise. Let's go turquoise. Ooh, what about some green? Last one, let's do green, a lime green. What do you think about that, Anderson?
Now I believe you. It really is a magic tea kettle.
So what I just did was not quite magic. It's just some pretty cool science. And I love this experiment so much because it's beautiful and colorful. There's a ton of chemistry going on. Anyone can try it at home. So pH is a key player in so many different aspects of our lives. And maintaining the right pH is crucial for everything from your body to the environment in our oceans, to even safely swimming in a swimming pool on a hot summer day. And having a good understanding of pH can help us answer questions like, why do I take an Alka-Seltzer when I have an upset stomach? Or why do I use toothpaste when I'm brushing my teeth? Have you ever thought about that before?
Well, yeah, actually.
Yeah, so some substances can be classified as either being an acid or a base. And you can think about them as sort of opposites of one another. And scientists can tell if something is an acid or a base by using a pH indicator. And a pH indicator is really just like a chemical compound that changes colors when it comes in contact with an acid or a base. So to make our pH indicator, we are going to use a simple red cabbage. And what we want to do is we want to extract this purple pigment that's found within the cabbage. And that pigment is called anthocyanin. And that's actually the same pigment that's found in the hydrangeas that you picked for your mom. So that pigment is you can use it as a pH indicator, meaning it will change different colors based on whether or not it comes into contact with an acid or a base. And we can do this a couple of different ways. We can extract this purple pigment a few ways. So we could use a blender, so that's what I have over here, and we can cut up this cabbage, throw it in the blender, and get that purple juice that way. Or we can boil the cabbage leaves. But today we're just gonna cut up our cabbage and we're gonna throw it in the blender and make us a red cabbage smoothie. Are you ready?
Oh no, I don't have to drink it, do I?
We'll see about that. So actually, I have already cut up some purple cabbage leaves to make it a little bit easier for you. So if you just want to throw those cabbage leaves into our blender.
Do we need all of them?
Sure, why not? Yeah, you can throw them all in there if you'd like.
I look like a mad scientist. It's like...
You do look like a mad scientist. Actually, that's probably good.
Oh, okay.
That's probably good, yeah. And then we'll need to add some water. So you want to pour this in there?
Into here?
Into here. Yes, into here. You can do it. There we go. I think that's probably good. All right, and so now we are going to blend up our purple cabbage. So you just want to press, you can, right, let's do high. You can press high.
Oh gosh.
Here it goes. Okay, so I think that this is pretty good. This is blended pretty well. And so now Anderson and I are gonna go filter out the big chunks that are left behind, and we will be right back. Anderson and I are back from filtering out our purple cabbage smoothie. Anderson may or may not have taken a big giant gulp of that purple cabbage juice. How was that experience, Anderson?
It was heartbreaking.
And probably a little gross, too. So what we have in front of us is we have our pH indicator. And as a reminder, this is just that purple pigment from our cabbage. And it's diluted into water, which has a pH of 7 on a scale of 0 to 14. So acids have a low pH, less than 7, and bases have a high pH, greater than 7. And when a substance comes in contact, or when a substance that's acidic comes in contact with that pH indicator, it's going to turn more of a pink color. So for example, a battery or battery acid is super acidic. And so if you got battery acid and you put it into this indicator, it would turn a bright pink or maybe even a red. But substances that are basic are going to turn more of a blue or green color. All right, and so here we have a bunch of household items, different substances, foods and drinks, cleaning solutions that we are going to test out to determine if they are acidic or basic. Are you ready?
I'm definitely ready.
Okay, first one up is we have this lemon lime soda. Anderson, do you think that this will be acidic or basic?
I think it'll be acidic.
Acidic? Okay, so what I want you to do is just pour it in that cup and give it a little stir and we will see.
Oh gosh. All of it?
You just keep pouring a little bit. Pour, there you go, that's pretty good. All right, what do we see? It is pink. So?
It's acidic?
It's acidic, yes, ding ding.
Oh yeah, one correct.
One correct, yes.
That's good.
Yeah, there you go. Good.
Thinking of word there.
Good job. All right, the next one that we have is a glass cleaner. Do you think glass cleaner will be acidic or basic?
Basic.
Basic, all right. Go ahead and pour it in there.
Oh.
Ooh, I love this one. Look at that, it is green. So Anderson was right, it is basic. And a kind of a good general rule of thumb is if bases are kind of slippery to feel, so a lot of soaps are typically basic.
Oh yeah.
Okay, how about this one? This is vinegar. Acidic or basic?
I think acidic.
Okay, test it out. You're pretty smart, Anderson. All right, let's see.
Yes.
Oh, look at you go. It is acidic. Oh, and look how pink this is. So would you say that this is more or less acidic than your Sprite?
Probably less.
Probably less? Okay, I would probably say it's a little bit more because it's more pink, right? So the pinker it is, the more acidic. But you could be right. All right, next one up. Ooh, this is a little tricky. So here we have some carbonated water, some sparkling water. Acidic or basic?
Oh. Acidic.
Acidic? Okay, go for it. Let's see.
I'm teaching my maths basic.
You can also say neutral. Okay, come on. Okay, so it's actually
neutral.
Yeah, it's slightly acidic, so it's a little bit pinker than the purple. So if it is neutral, it would just be this purple color. So it is slightly acidic. This one was a tricky one. Yeah. All right,
No.
How about this sour candy? Do you like this stuff?
Not exactly.
Sour candy, acidic or basic?
Acidic.
Acidic, okay.
Yeah.
Oh, very, very, very acidic. All right, good job. All right, next one up is baking soda. So this is a little bit different because it's not a liquid, it's a powder. But do you think it'll be acidic or basic?
I think acidic.
All right, let's test it out. Oh, look how pretty this one is. So it is blue. Very, very pretty. So blue, acidic or basic?
Basic.
Slightly basic, or actually it's a good bit basic. Okay, the next one, this one is pretty cool. So now we have toothpaste. But before we add the toothpaste, I want you to think about this, and our viewers at home can make this prediction as well. So what does your dentist always tell you is bad for your teeth?
Candy?
Candy and soda, right? And that's because those are really acidic, right? We just saw that the soda turned a bright pink and that candy turned a bright pink. And so what do you think toothpaste would be if your dentist says that those things are bad for your teeth because they're acidic?
Basic?
All right, well, let's give it a shot. So you're just gonna squeeze that into this cup. That's good, that's funny. All right, and we will stir this one up.
Minty fresh. Wonder if we can put like a ding in there. It's just like minty fresh. Ding. Ding. Say ding. Say it.
Ding. Okay.
It worked out.
So it turns out that toothpaste is slightly basic. And so the normal pH range of in your mouth is somewhere between 6.2 and 7.6. So relatively neutral, like water. But food and drink can lower the pH of the saliva or the spit in your mouth. Because when you, so for example, when you eat a bag of Doritos or you chomp down on a quarter pounder, the bacteria in your mouth are going to start to break down those carbohydrates. And as they break down those carbs, acids like lactic acid, aspartic acid, and other acids are going to be released, lowering the pH level of your saliva. And so by using toothpaste, we're sort of counteracting that to bring that pH level of your mouth back to more of a neutral, healthy state. Because whenever the pH level in your mouth gets too low or too acidic, those acids are going to start to demineralize or to break down the enamel on your teeth.
So to put it simply, toothpaste takes the sweets away.
There you go. Exactly right. Okay, how about this one? This one is laundry detergent. Acidic or basic?
Basic.
Okay, give it a shot. Ooh, I love this one. Look how pretty this one is. This is a bright lime green. So Anderson, you were right.
Yes, I don't know how many I got right so far, but I feel the power.
He feels the power. All right, and so we're going to leave one as our control because remember, this is neutral, so this is 7. So the last one that we're going to test, and this one is kind of my favorite, this is egg white. Do you think that egg white will be acidic or basic?
Probably acidic.
All right, let's give it a shot. So you'll pour that in there. All right, we'll stir it up. So it turns out that egg white is a little basic. And so look at that beautiful green. And so if you're feeling a little bougie, I don't know, maybe get some cabbage juice and add it to your eggs, and there you go. You have green eggs and ham.
I wouldn't recommend using cabbage juice.
Maybe just a little bit, and it wouldn't taste so gross. But again, I love this experiment so much because it's beautiful, colorful. Anyone can try it at home. And I would encourage you guys to test out other substances. You don't have to just test vinegar. Test out coffee. Test lemon juice. The world is your laboratory.
So what you're saying is you can basically try out anything.
That's right, Anderson.
Hello, my name is Shreya, and I was wondering why the ocean is blue. The main reason the ocean is blue is the way water molecules absorb and scatter the colors of sunlight. The ocean looks blue because red, orange, and yellow, which are the long wavelengths, are absorbed more strongly by water than the blue, which is the shorter wavelength. So when the white light from the sun enters the ocean, it's mostly the blue that gets returned. Same reason the sky is blue. The ocean may also take on green, red, or other hues as light bounces off or floating sediments and particles in the water take control.
Welcome back to Alabama Swim Explorers. We just did an experiment with red cabbage and we made a pH indicator. We used regular household items and tested them to see if they were basic or if they were acidic.
Right, and so when we added our pH indicator to the acids, it turned more of a pink color, and then when we added them to the bases, it turned more of a blue or green color. And so now what we're going to do is we're going to take what we learned in that last experiment, and we're going to apply it to a real-world situation. And we're going to explore the science behind ocean acidification. So as our world industrializes and we continue to burn fossil fuels, and fossil fuels are things like oil and coal and natural gas, as we're burning these fossil fuels, they are emitting a lot of greenhouse gases into our atmosphere. And the greenhouse gas that we're going to talk about today is carbon dioxide. And you've heard of carbon dioxide before, right?
Yeah, that's what we exhale.
That's right, and so most people are familiar with carbon dioxide because it's one of the products of cellular respiration. So you inhale oxygen, a couple of reactions are going on, and then you exhale carbon dioxide. But carbon dioxide is a greenhouse gas that is leading to our oceans becoming more acidic. And we're going to do a couple of experiments to look at that, because don't just take my word for it, Anderson. I love to experiment and I love to test things out to see if it's really right. So what I have in front of us is a model ocean. And this ocean has a neutral pH because it is just our pH indicator in water. And oceans are really salt water, but that's really not going to play a role in this experiment. And so here's our model ocean. And then over here, Anderson, I have a lot of different supplies that we can use. And we're going to use these to introduce carbon dioxide into our ocean. So based on what you see, what do you think that we could use to introduce carbon dioxide? So we have some baking soda, vinegar, this is some dry ice, and then we have some drinking straws.
I know we're not really supposed to do this, but I think we can get straws and blow bubbles in the ocean.
That's a great idea. So here are some drinking straws. I will give you this green one, and I am going to take this yellow one.
I love the color green.
I know you do. So here is Anderson's ocean, and here is my ocean. And remember, this is going to be our control ocean, so we are not going to introduce carbon dioxide into the control ocean. So what Anderson and I are going to do is we're going to take our drinking straws, and we're just going to blow bubbles, and we're going to exhale this carbon dioxide and see if we can make our ocean turn pink. Because remember, if carbon dioxide is really making our oceans more acidic, and this is a pH indicator, we should see our ocean also become more acidic, and it should turn pink. Are you ready to go?
Oh yeah.
All right, let's see who can make it the most acidic. All right, on your mark, get set, go. Man, that is a lot of breathing, a lot of bubbles. Let's check it out. Let's look at our oceans. They are pretty pink. Check that out. Look at that. So we, based on this investigation, we can see that exhaling that carbon dioxide, introducing carbon dioxide into our ocean like this, definitely making it more acidic. And I say that mine is a little bit more pink than yours. I always knew you were a little basic, Anderson.
Oh, Kathryn. You know what I think you should do?
What?
I think all the viewers at home want to see you drink it.
I don't think so. Maybe after the fact. Okay, no, that would be gross. That is something we definitely don't want to try at home because it's pretty stinky. Okay, Anderson, so we have tested out the straws. What is something else that we could do to introduce carbon dioxide into our ocean?
We could use the vinegar and the baking soda.
That's right. So yeah, vinegar and baking soda, whenever you mix those two together, one of the products is carbon dioxide. So I am going to grab this, And again, same color because we're starting over, so the pH level is the same. And what I've done, if our viewers at home want to try this out, I've just gotten like a bathroom cup with some tape, and I've taped it to the inside of our cup. And now, Anderson, will you measure 1 teaspoon of baking soda and just put it into that cup?
Oh goodness. This is about 1 teaspoon, right?
That's pretty good.
Oh,
there you go.
Don't fall, little cup.
And now you don't want to add a ton of vinegar because you don't want it to bubble over, but we'll just add just a little bit.
Oh.
It bubbled over a little bit. That's okay. So now, as this reaction is happening, carbon dioxide is being produced in those bubbles. We capped it off so we could trap that carbon dioxide gas in our ocean. And then I really like this one a little bit better because before, when we were blowing those bubbles with the straws, you were just blowing carbon dioxide straight into the ocean. There are not giant straws in our oceans that are introducing carbon dioxide that way. That's really not how it works. It's more of a slow diffusion. And so in this experiment, it takes a little bit longer, but whenever you try it at home, you can start to see just a really thin pink line at the top of the ocean. Do you want to check it out, Anderson? Do you see that thin pink line?
Yes, it's really small though.
It's really small. And as this experiment goes a longer period of time, then your entire ocean is going to start to turn pink, and you can really see a gradient. And so I did this earlier just to show you guys. And so this is after about 30 minutes of the carbon dioxide being produced and dissolving into the ocean. That's pretty cool.
That is really cool. And I think that this really explains how carbon dioxide gets into the oceans.
That's right. Yeah. So we have carbon dioxide. Whenever it interacts with water, you're going to get carbonic acid. And then there's a lot more downstream effects that'll happen with marine life. So for our last experiment, Anderson, we have one more ingredient over here that we could possibly test out. You want to throw that over there?
Okay. I'm not going to actually throw it. That would be kind of weird. Do we need this still?
Yes, so this is our model ocean. So we have tested our straws, we've tested the baking soda and the vinegar. What do we have left?
The dry ice.
The dry ice. And so dry ice is actually just frozen carbon dioxide. It's frozen gas. And so as this carbon dioxide warms up, it sublimates and it goes straight from a solid to a gas. And that gas is carbon dioxide. And so we could do this experiment a couple of different ways. We could use a bathroom cup like we did before and let it slowly diffuse, but I don't know. I think we should just throw it in. What do you think?
Oh yeah.
Yeah, that's always a little bit more fun. So here is our ocean. So remember, to our viewers, we are comparing pH of 7, neutral. And now let's see what happens when we add our frozen carbon dioxide gas. You ready?
Oh yeah. Oh wow.
Now take a look. I know the fog is really cool, but take a look at that color change. We'll kind of move it away from our model ocean. Do you see how it's becoming lighter? It's becoming more pink.
Oh yeah, I do see that.
Yeah.
So when dry ice starts melting, it doesn't turn into water, it turns into gas.
That's right, yeah. So the dry ice is just frozen carbon dioxide, and so it goes through a different sort of process. It never changes into a liquid at atmospheric pressure. It just goes directly from a solid to a gas.
Thanks for watching Alabama STEM Explorers. If you missed anything or you want to watch something again, you can check out our website at alabamastemexplorers.org. Maybe you have a question we could answer here on the show, and you might grab a cool t-shirt. Feel free to send us a video question or an email on our website, alabamastemexplorers.org. Thanks again for watching. We'll be back next week.
Alabama STEM Explorers is made possible by the generous support of Hudson Alpha Institute for Biotechnology, translating the power of genomics into real-world results. Southern Research, solving the world's hardest problems. The Hawley Family Foundation, established to honor the legacy of Brigadier General Everett Hawley and his parents, Evelyn and Fred Hawley, champions of servant leadership. Alabama Works, a network of interconnected providers connecting business and industry needs to a highly skilled and trained workforce. Alabama STEM Council, dedicated to improving STEM education, career awareness, and workforce development across Alabama. Alabama Mathematics, Science, Technology, and Engineering Coalition for Education, advocating for exceptional STEM education in Alabama. Alabama Math, Science, and Technology Initiative, the Alabama Department of Education's initiative to improve math and science teaching statewide.